Biomedical waste management. Introduction. The waste generated from the hospital carries a higher potential for infections and injuries. Therefore, it is essential to have safe and reliable methods of segregation and disposal of hospital waste. Definition. Biomedical wastes are defined as wastes that are generated during the laboratory diagnosis, treatment or immunization of human beings or animals, or in research activities pertaining thereto, or in the production of biologicals. Waste generated in hospitals. In developing countries, the waste generated in hospitals falls into two categories. General, non-hazardous solid waste, 80%. Biomedical waste. This includes infectious waste, 10%, and chemical, radioactive waste, 10%. Hazards associated with BMW. Hazards from infectious wastes. Pathogens in the infectious waste. Hazards from infectious sharps. Hazards from chemical wastes. Hazards from pharmaceutical waste. Hazards from cytotoxic waste. Hazards from radioactive waste. Waste management hierarchy. The waste management hierarchy is largely based on the concept of the 3R, namely reduce, recycle and recover. If none of these methods is available, then the last method opted is disposal. 1. Prevent and reduce. The most preferable approach is to prevent or reduce the production of waste as far as possible. 2. Reuse and recycle. The next best option is to reuse the waste as such or after recycling. 3. Recover. Where practicable, recovering waste items for secondary use can be done. 4. Treatment. Wastes that cannot be recycled or recovered can be subjected to treatment by various methods such as incineration. 5. Disposal. It involves disposal of the waste in landfill or dump yard. This is the least preferable option among all waste management strategies. Biomedical waste rule. In India, the Ministry of Environment and Forests has formulated biomedical waste rule in 1998. There are 5 categories of biomedical wastes. There was considerable overlapping between categories which created ambiguity and confusion. The new Biomedical Waste Management Guideline was published in 2016 with an amendment added in 2018 and 2019. According to this new rule, there are 4 categories of biomedical wastes, each is segregated by a single color-coded container. Steps of BMW management. The management of biomedical waste can overall be summarized into 6 simple steps. 1. Waste segregation, at the point of generation, into color-coded containers. 2. Pre-treatment for laboratory liquid waste. 3. Transport of waste from generation site to central storage area of the hospital. 4. Transport of waste from central storage area to common biomedical waste treatment facility. 5. Treatment. 6. Disposal, within 48 hours of generation. 1. Waste segregation in hospitals. Waste segregation refers to the basic separation of different categories of waste generated at source in the hospital and thereby reducing the risks as well as the cost of handling and disposal. According to Biomedical Waste Rule 2016, segregation of waste should be done by using containers of 4 different colors, each is designated for segregation of a particular waste category. Yellow for infected wastes. Segregate soiled, anatomical, chemical, liquid laboratory waste, expired and discarded mediums in yellow container. Red for infected plastics. Segregate syringes, gloves and plastic wastes in red container. White or translucent sharp container or puncture-proof box, for metal sharps. Blue container, puncture-proof box, for broken glass items and metal implants. Importance of segregation. Segregation is the most crucial step in biomedical waste management. Wrong segregation may lead to serious consequences such as needle stick injury transmitting hepatitis B or HIV, if sharp items are segregated into yellow or red bags. Production of carcinogens, if plastic items are wrongly segregated into yellow bag and subjected to incineration, leads to production of carcinogenic furans. 2. Pre-treatment. The laboratory liquid waste should always be pre-treated either with chemical example 1 to 2% hypochlorite or autoclave before segregating into appropriate containers. 3. Transport. The waste should be transported within 24 hours by dedicated trolley to the central biomedical waste storage facility of the hospital. Separate routes should be used for transport to prevent exposure to staff and patients and to minimize the passage of loaded carts through patient care and other clean areas. Storage of the waste at ward is strongly discouraged. Central storage area. This is a temporary storage facility present within a hospital where different types of waste should be brought for safe retention until it is treated or collected for transport to common biomedical waste treatment facility. Personal protective equipments for handling biomedical waste during transport or in the storage area should wear appropriate personal protective equipment such as heavy-duty gloves, 3-ply masks, gowns and gumboots. The following general principles need to be followed during segregation, transport and storage of biomedical waste. Waste receptacles. The waste receptacles should have the following properties. Plastic bags must be labeled with biohazard logos and should be non-inflammable, autoclave stable and non-chlorinated with a thickness of greater than 50 micrometers. Containers should have well-fitting lids, either removable by hand or preferably operated by a foot pedal. Sharp box should be puncture-proof, leak-proof and tamper-proof impermeable container. Securement. All the bags used for waste collection need to be sealed once they are filled to 3/4 of their capacity. Labeling. Bags and containers should be labeled properly with the date and place. 4. Transport of waste to common biomedical waste treatment facility. Transport of waste from central storage area to common biomedical waste treatment facility. Indian Medical Association goes eco-friendly is a common biomedical waste treatment facility at Palakkad, established by Indian Medical Association, Kerala State Branch. Image provides comprehensive service to all private healthcare institutions by executing the complete cycle of biomedical waste disposal. Regular collection of biomedical waste from affiliate healthcare institutions in barcoded color, coded bags, transportation in specially designed dedicated vehicles. 5. Treatment. As per the mandate of the Biomedical Waste Management Rules, 2016, the final disposal and recycling must be performed at common biomedical waste treatment facility. Only when there is no common biomedical waste treatment facility within 75 kilometers, the hospital can create its own disposal facility. The following are the methods used for treatment or disposal of biomedical waste. A. Incineration. B. Autoclave. C. Chemical disinfection. D. Effluent treatment plant. A. Microwaving. F. Hydroclaving. G. Plasma pyrolysis. A. Incineration. Incineration is a high-temperature dry oxidation process that reduces organic incombustible waste into non-organic incombustible matter, resulting in a very significant reduction of waste volume and weight. Incineration is usually done for those wastes that cannot be reused, recycled or disposed of in a landfill site, for example human and animal anatomical waste, microbiological waste, and solid non-plastic infectious waste. Halogenated plastics such as PVC should never be incinerated as it generates furans which are carcinogenic. B. Autoclave. Autoclaving is a thermal process where steam is brought into direct contact with waste in a controlled manner and for sufficient duration to sterilize the wastes. It is mainly used for the treatment of infectious plastic and sharp waste. C. Chemical disinfection. A chemical such as hypochlorite 1 to 2% is mixed to waste which results in disinfection. It is more suitable for liquid waste such as discarded blood and body fluid and also for hospital sewage. D. Effluent treatment plant. The liquid waste generated in the hospital if mixes directly with groundwater it can create significant health risks. Therefore, it is first subjected to chemical treatment and then is drained into effluent treatment plant. ETP removes the suspended solids and organic matter in wastewater and then disinfects the wastewater with hypochlorite and finally drain the water to municipal drainage. A. Microwaving. Microwaves are radio frequency waves, used at a frequency of 2450 MHz. They produce friction of water molecules which generates heat. Large-size microwaves are used for disposal of biomedical waste, mainly infectious plastics and sharp wastes. F. Hydroclaving. Hydroclaving is a low-temperature steam sterilizer, involving steam treatment with fragmentation and drying of waste. It breaks up the waste into small pieces of fragmented material, thus obviates post-cycle shredding. G. Plasma pyrolysis. Plasma pyrolysis uses ionized gas in the plasma state to convert electrical energy to temperatures of several thousand degrees using plasma arc torches or electrodes. The system provides temperatures combined with high UV radiation flux which destroys pathogens completely. 6. Disposal methods. A. Shredder. B. Deep burial. C. Shark pit. D. Encapsulation. A. Inertization. A. Shredder. Shredding is a process by which wastes are shaped or cut into smaller pieces so as to make the wastes unrecognizable. It helps in prevention of reuse of BMW and also helps to reduce the waste volume. B. Deep burial. Deep burial is a pit dug about 2 meters deep. It needs to be half filled with waste, and then covered with lime within 50 centimeters of the surface, before filling the rest of the pit with soil. The groundwater level should be a minimum of 6 meters below the lower level of a deep burial pit. C. Shark pit. A shark pit constructed within the hospital premises provides an alternative method for disposal of the shark wastes generated from the facility. D. Encapsulation. Encapsulation method involves filling the containers with waste, adding immobilizing material and sealing the containers, to prevent the access to unscrupulous activities. The process uses cubic boxes made up of metallic drums which are 3/4 filled with sharks or chemicals or pharmaceutical wastes and then filled with a medium such as plastic foam, cement mortar or clay material. Inertization. The process of inertization involves mixing waste with cement and other substances before disposal to minimize the risk of toxic substances contained in the waste migrating to surface or groundwater. It is especially suitable for pharmaceuticals and for incinerated ashes with a high metal content. Disposal of cytotoxic drug waste. Expired cytotoxic drugs to be returned back to the manufacturer or supplier or common biomedical waste treatment facility for incineration. Disposal of general waste. They constitute the large component of hospital waste. They are not biomedical waste. Their disposal can be carried out by several strategies. Composting. It is the decomposition of organic matter by microorganism in warm moist environment. Waste to energy. By various methods such as incineration, pelletization, biomethanation, etc. Recycling of the waste. Landfilling in dump yard. It is the least preferred method. Monitoring of biomedical waste management. Monitoring is an essential component of managing biomedical waste in the hospital. Biomedical Management Committee should be formed in a healthcare facility, which serves several functions. To oversee the implementation of biomedical waste practices. To educate healthcare workers about biomedical waste management practices. To monitor biomedical waste management in a hospital. Monitoring of biomedical waste management practices can be carried out through the following ways. Biomedical waste segregation audit by direct observation. Biomedical waste segregation audit by CCTV camera. On-site inspection of biomedical waste segregation at common storage area. Conducting surveys through structured questionnaires. Barcoding-based tracking of biomedical waste, starting from segregation to disposal.